Hello, this is Group 26's final demo. This project is the Breaker Energy Automation and Management System, also known as BEAM. The members are Tristan Palumbo, Anika Zheng, Hugo Tarira, and Nicholas Rubio. It's comprised of 3 electrical engineering majors and a computer engineering major. This automatic circuit breaker unit will be able to remotely control circuit breakers, detect grid instability, improve power efficiency, and be easily installed. We aim to meet these requirements by creating BEAM. BEAM is comprised of 2 units, the motor system and the frequency detection system. Both of these are controlled through a mobile app and will be demonstrated throughout this video. Here we have the demo requirements, and we have 3 main ones that we are going to be focusing on for this demo. The first requirement is to have at most a 5% error on the physical switching of the circuit breaker, which is a 95% success rate. The second requirement is to have at most a 1% error in frequency detection accuracy. And the third requirement is a max system response time of 20 seconds for each of the switches. The other requirements shown are the switching force, max frequency detection reaction time, the max power consumption, and the thermal output of the PCBs. These are also important but will not be explicitly demonstrated in this video. Here is the motor system design for BEAM, and in the bottom right you can see the DC linear actuator, which is one of the motors we are using and is responsible for the physical switching of the circuit breaker along with its 3D printed attachments. The second motor we are using in the top right is the linearly guided stepper motor and is responsible for moving the actuator to different circuit breakers across the panel. The table below shows what each of the colored bubbles represent. The red bubble is the linearly guided stepper motor, green is the DC linear actuator, and orange is the circuit breakers. The black filament parts on the DC actuator are its attachments that I mentioned.
Moving on, we have the motor system housing, which includes the motor unit PCB and the 4 lithium-ion battery bank, which goes from a minimum of 12 volts to about a maximum of 17 volts when fully charged. As you can see on the top right, we have the connection for the PCB to the lithium-ion battery bank. And on the bottom left, we have the connection to the DC motor. And on the middle left, with the 4 colored wires, we have the connection to the stepper motor. Highlighted here are the 3 regulator breakout boards. For the 3 regulator input voltages, they are all connected to the battery, which ranges from 12 volts at minimum charge to 17 volts at full charge. The bottom right regulator is a 10-volt regulator that is used to power the DC motor. The middle regulator is also a 10-volt regulator, but it's used for powering the stepper motor. The top right regulator is a 3.3-volt regulator that is used to power the ESP32 and its peripherals.
Finishing off the motor unit PCB, we have the motor driver breakout boards. The red bubbles indicate the 2 motor drivers that control each motor in the system. The first one on the top is the stepper motor driver, which uses the DRV8825 chip, and the second one on the bottom left is the DC motor driver, which uses the DRV8833 chip. The purpose of making these breakout boards is to be able to easily replace them if they become damaged instead of replacing the entire board.
This is the frequency detection system design. On the far bottom left, we have the cable from the outlet connecting to the primary side of the power transformer, stepping down 120 volt to 4.5 volt RMS, or around 6.4 volt peak. This is followed by AC to DC rectification in a full wave center tap configuration in the bottom right. We also have our 3.3 volt regulator to power the ESP32. Lastly, we have a voltage divider and DC bias circuit connecting to the ADC input of the ESP32 to properly obtain a scaled sine wave voltage from the secondary side of the transformer for Fourier transform processing, which is used to determine the frequency of the grid.
Now that we're finished explaining how BEAM works, it's time to show you. As you can see, we have an app that displays the different switches that are numbered on the breaker panel. They are numbered from right to left on the painter's tape, with the far right breaker being circuit breaker 1 and the far left being circuit breaker 4. The tests that are run during this video showcase our system requirements, and this one is making sure that the correct circuit breakers are operated when desired.
So here we want to showcase the control page of the app and how the user can actually manually control and flip the different breakers on their breaker panel using BEAM. And so kind of looking at the page, the control page on the right side here, we can see that for every breaker, we have a breaker tile which consists of a status indicator as well as a switch button on the right, as you can see. And so regarding the switch button, the user simply needs to press that button in order to send a command to flip a breaker to the position that it's currently not. So if it's on, if you click it, it'll flip it off, and vice versa. The status indicator is actually updated in real time from the hardware of the system. So the hardware stores what the breaker states are, and so that way if the app ever disconnects or reconnects, it retrieves those breaker states from the hardware, so that way everything is always synced up. And so as you can see, when a command is called to flip a breaker on or off, a loading overlay appears with some text indicating which breaker is being flipped. And if that command is successful, we can see that the status indicator and the switch button also update in real time to the new change that happens. Another thing to note with this loading overlay is that when that overlay is on the screen, the user is not able to click anything. Purpose of this is so that way the user doesn't send multiple commands at the same time. So one breaker command can be processed at a time, and if for some reason a command fails, we do have notifications on the bottom of the screen that will pop up in the event that a breaker flip fails, and it will give context as to the failure to help the user diagnose the system and figure out what exactly happened.
Here's the frequency detection unit and its housing that we made. The wires from the power cord were covered using liquid electrical tape for safer operation.
Here we are demonstrating the frequency detection functionality. On the left, we have a signal generator to simulate different grid frequencies, and on the right, the mobile app shows the frequency value to the user. It takes a measurement every 4.3 seconds, giving it a resolution of about 0.23 Hz. This means the error between the true frequency and the measured value should be no higher than 0.12 Hz. Here, we lowered the frequency to 61.2 Hz, and on the app it shows 61.17 Hz, which is an accurate measurement. The frequency detection unit sends the frequency value to the motor unit, which acts as the server. The motor unit then forwards that value to the app. The frequency detection unit only sends updates when there's a change in the grid frequency. This is to reduce power usage on the motor unit so the motor unit isn't constantly receiving unnecessary updates.
So here we want to showcase the automatic frequency response of the system. So to start off, the user has the ability to customize which breakers will get flipped on a frequency drop. So right there, the different breakers were selected, 1, 3, and 4. So when that frequency drop occurs, we expect those 3 breakers to flip off and remain off until the grid returns back to normal. And so just to showcase the systems page further here, as we update the frequency on the waveform generator, we can see that the app sees those changes and displays them in real time with very low error. And so once we drop that frequency to 59.4 Hertz or less, the system is going to detect that as a critical frequency drop, and in response to that, it will carry out the automatic frequency response. So as you can see here, we drop the frequency to that threshold, and so on the control page, this overlay appears showing that the grid is unstable because of a frequency drop, and the system, as you can see on the left, is carrying out that response of flipping breakers 1, 3, and 4, since those were the 3 breakers that the user set on the settings page. If the user wants to set any combination of breakers on or off, they are able to fully customize this response that you are seeing here through that page, and when those settings are saved, they are saved in the hardware for the system to refer to. And this overlay is going to stay here until the grid returns back to normal, because we don't want the user to be able to flip things back on when the grid is unstable. As you can see, since the grid has been stabilized, another overlay appears, allowing the user to press a button to restore the breakers to the state that they were in before. So basically undoing that frequency response and returning to our original state. It's important to note here too that the user is required to restore the breakers after a frequency drop. We don't want to automatically flip breakers back on when the grid returns to normal because there are safety electrical concerns there. And so when that grid stabilization has happened, the user does need to tell the system to restore the breakers so that we can return to normal operation.
The 3 tables below show the results and data for the 3 main requirements of Beam. The first table on the top left shows the percentage of error or the successful switching that the main motor unit has. Here I put the number of times each one of the circuit breakers was switched during this video, but a lot more testing was done off camera. There was a 0% error and all the switches were successfully switched. The second table on the right shows the percent error for the frequency detection. Earlier in the demo, we tested the accuracy and the percent error was calculated to be always less than 1%, which satisfies the second requirement. And finally, on the bottom left, we have the total system response time for each switch, which was measured with the on-screen stopwatch. This concludes our final demonstration of Beam. Thank you to our sponsors, Professor QZ Sun at UCF and Guanyu Tian at Texas A&M Galveston. Thank you for watching.